Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 34. So it's always a good idea to never get lost in the midst of details as we put together all the details in search of a coherent bigger picture. Now what is a bigger picture in this course? The biggest picture in fact is to understand astrochemistry, right? And for that we are in this stage where we're trying to see how do we detect molecules in space being on Earth, right? As part of it, we understood that to detect molecules in space, we have to have an idea about how light and matter interact with each other. Because ultimately, it is light from star or from a distant galaxy that reaches us, and it is through this light that we gain information about the chemical composition and molecules present in space. All right? Okay. So that said, to understand light-matter interaction, we should first know what light and what matter are, correct? So we had a brief idea about what light was. I said that light was both a wave and a particle, and that it exhibited wave-particle duality. And as part of it, we even saw what waves and particles are. And we looked at the key distinctions between waves and particles, all right? And we also looked at matter, right? And matter as relevant in astrochemistry. We're talking about the electrons, atoms, molecules, etc., whose dimensions are roughly, within like 10 to the power minus 8 meters. Okay, right? Now, these are all molecules and species which exhibit wave-particle duality yet again. All right? So, these exhibit wave-particle duality, and such matter are called as quantum mechanical systems. Okay, right? These entities, which are roughly of this order of magnitude, whose dimensions are of this order of magnitude, right? 10 to the power minus 8 meters, and they exhibit wave-particle duality. They are called as quantum mechanical entities. Now, we saw that to describe the motion of these quantum mechanical entities, which is again very helpful to understand light-matter interaction, we have to include both wave nature as well as particle nature. And in the previous lecture, previous few lectures, approximately lectures 32 to 33, roughly, okay, right? We were looking at how we can start with the wave equation and obtain what is called as the time-independent Schrodinger equation, right? To describe the motion of these quantum mechanical matter. All right, this is where we are at. So I again want to emphasize on the interdisciplinarity of this course. Recall that to understand astrochemistry, right, we must have a firm footing in chemistry to understand the type of molecules and the chemistry of molecules happening in space. But not just that, we must also complement and substantiate that with a thorough knowledge of classical mechanics, quantum mechanics, spectroscopy, etc. So it is in that part. That we are at in this course. Okay. So in the previous lecture, that is in lecture 33, we had obtained this equation. We had obtained this equation: H psi equals E psi, right? Where H I showed was nothing but minus H bar square by 2m. Where m is the mass of the quantum mechanical entity, and h bar is h over 2 pi times d square by dx square for a one-dimensional system, right? For an n-dimensional system, the same idea can be generalized. It's very easy, so that's not a big deal at all. Okay, so I'll just keep exactly the one-dimensional the parameter that we had obtained in the last class. Okay, this plus some potential, the form of which we don't know yet. Okay, right? It depends on the system. Okay, so this is the H, and your psi, which is a function of your psi of x, okay, which is a function of your direction along which the motion is happening, right? Now that is a purely mathematical purely mathematical function or entity. I'll put it this way. In other words, you cannot perform any experiment whose output is going to be the wave function. This is a very important, a subtle point which gets lost oftentimes. Okay, so please note it. And using this mathematical function, which is also called as the wave function, we obtain, we solve this equation. We solve for this equation and obtain the energy. Okay, right? Energy, which is the physically observable in other words, you can perform experiments to get the energy of a system. Okay, right? So, and of course, the SI units of energy is joules. So this is what we saw in the last class. So in today's lecture, we shall be continuing from this particular equation. See one more variation of this equation, right? And look at some other aspects of the equations used to describe quantum mechanical systems motion, right? Which will be helpful to understand the various aspects of spectroscopy. In other words, the various aspects of how and where we get spectral signals. Why are they discrete and not continuous? Remember, right? Whenever we have been discussing any spectrum, be it the spectrum obtained from sun, the solar spectrum, the Fraunhofer lines, or when we discussed about the microwave radiation or the electronic spectra of CH plus CH and CN, the first few molecules to be detected in space, right? The lines, the spectral lines or the spectral signals we obtained were all discrete. Okay, right? Were all discrete. They were not continuous. Now, why they were discrete? I told you that, like I shall give the answer after a few lectures. We are close to that stage where, I can give you the answer. To understand precisely why they are discrete, we shall look into just a little more quantum mechanics. Not a whole lot, but a little more. All right? Yeah. Now, before proceeding any further, you look at this equation. Okay, you look at this equation. If you think about it, if you think that like this equation is any really fancy equation, which looks, which looks menacing, right? Don't worry too much about it. Okay, right? In fact, this whole equation is nothing but it's recasting this equation. Your H psi equals E psi, right? I've just put a hat atop it. This is called as a hat, right? I put a hat atop this H to just indicate that I'm not talking about the hydrogen atom or something like that. Okay, right? This is what is called as, an operator. Don't worry too much about the jargon. Okay, I have not told you what an operator means. It's just that, some mathematical operation we're performing on some function. Okay, to indicate that this is an operator, we are just including a hat. Of course, more details will follow in any quantum chemistry course. For our purpose, this detail is enough. So don't worry if you don't understand what precisely an operator means. We don't even care about it in this course. All right? Okay. So what this particular statement means, okay, right? In effect, it just tells you that, see, recall in the last lecture, I had told you that your kinetic energy, which is P squared by 2m, where, like your P is P of x, right? Where your P is P of x. In other words, the momentum changes with the position, correct? So that is P of x, and your potential energy, whose quantum mechanical correspondence is minus h bar square by 2m d square psi of x by dx square. So this term, right, is exactly the same as this, all right? And your potential energy is given by V of x. So you folks understand, right? You understand where we are coming from? So therefore, you have the potential energy and kinetic energy, and the sum of this, right? The sum of this is going to be a constant E. There is an x dependence in both of these terms, right? In other words, the kinetic energy and in the potential energy, there is an x dependence, but the total energy is a constant. And therefore, that the sum of potential energy and kinetic energy for a system which is not under the influence of any external force is a constant, right? This equation is just, it's the quantum mechanical version of the conservation of energy. All right, are we clear? So this h psi equals E psi overall simply implies, okay, right, conservation of energy for a quantum mechanical system at any given point, any given point of time, or I'll just put it at any given time. Are we clear? So what did we do? We just gave a quantum mechanical version to the conservation of energy statement, which is so commonly prevalent in classical physics, right? In fact, it is the whole idea of conservation of energy, right? And the conservation of momentum, not just the conservation of energy, but also the conservation of momentum, which gives rise to a disk shape for all the, all the debris that is coming out of the star as a protostar is getting formed. Recall how we know the comets, meteorites, etc., were formed long, long ago. I was telling you that there is going to be a circumstellar disk, right? Why should that be a disk? That disk is formed in accordance with the principles of conservation of angular momentum. Okay, right? So likewise, right, here there is conservation of energy. Okay, so the quantum mechanical version of a conservation of energy is nothing but the statement h psi equals E psi. Are we precise? Okay, are we clear? So the whole idea, ideas of classical physics are mostly translatable to the ideas in quantum mechanics also. Okay, right? We saw the conservation of a few quantities in the formation of a protostar. Although I didn't tell you explicitly, that like the angular momentum is conserved, etc. We could perhaps, see it in a subsequent tutorial. I could give you some exercises based on that. So the same ideas, conservation of various things. When we talk about elastic collisions, inelastic collisions, etc., which shall be coming forth more, when we discuss light matter interaction, right? So this conservation principle is very much valid in the quantum mechanical realm also. Okay, and notice an important point I've given. It is that at any given point of time, this is going to be valid. Now, it is very natural for you to ask me one question at this stage. It is that, okay, I've given this equation, this is all fine, but I'm saying that, this is an equation of motion. This is an equation of motion, right, which describes how quantum mechanical entities move, right? Now, the minute, I say an equation of motion, there should be some time dependence, right? Where is the time dependence? Where does t come in h psi equals E psi? Right? It's a very natural question, right? The minute I say motion, right? Okay, conservation of energy is fine. Conservation of energy at any instant is fine. Okay, right? But what about time? After all, in almost all of my classical equations of motion, even in F equals ma, right, there is always a time derivative. In other words, something is differentiated with respect to time. Something changes with respect to time. It could be your velocity, it could be your acceleration, it could be anything, right? It could be your distance. Okay, so in the whole picture, time doesn't appear at all. Correct? Are we clear? Right? You understand? Despite this equation being the quantum mechanical version of conservation of energy, it doesn't give us any information about how a quantum mechanical system evolves with time. Are we clear? Okay. Now, therefore, the same problem that is besorting us right now was also confronted by the person who devised this equation. He was Schrodinger. Okay, right? So initially, he started off with the wave equation, and then he gave us this Schrodinger equation. This is called as the time-independent Schrodinger equation. Of course, because t does not appear anywhere here. He later on understood that, okay, there has to be some time dependence somewhere, right? So this equation had to be, somehow accommodate time also. All right. And by the structure of this, looking at the dimensions, right? Looking at the dimensions, whatever be the unit of your wave function, right? The h and d, this is going to be energy, and this is also going to be energy. So there is no way you can actually incorporate time directly into this equation itself. Okay. So Schrodinger thought about it. Okay, Schrodinger thought about it, and he came up. I again emphasize on the use of the phrase came up. Okay, he came up and proposed one more equation. I'll delete this part. Okay, so to understand time evolution, I mean, when I say no time evolution, I'm just describing how the coordinates of any system, any quantum mechanical system changes with time. That's what I'm calling as time evolution. Okay, right? Time evolution of a quantum mechanical system. Schrodinger, okay. Right? Proposed or came up with yet another equation, right? Which is called as the time dependent Schrodinger equation, which is given by I h bar is equal to h psi. Are we fine? Okay, so this is the equation that he proposed. Now notice this. I will just describe the features, and notice this. He proposed it. Okay, right? He never derived any equation. Okay, he never derived any equation. Even HI equals ESI was not derived. It was just, you started off with the wave equation and incorporated particle nature by including the de Broglie relationship. Okay, now likewise, Schrodinger just thought about, like how to include time evolution, and he proposed this system. It cannot be derived, not derived. It cannot be obtained neatly even from the wave equation itself. Okay, so I'll just give it to you as such. So note that whatever I did for the time independent version, that is to go through a few steps starting from a wave equation. One cannot do such a straightforward thing for this particular equation. All right, Newton just gave it as such. Okay, of course this is based on analogy starting with the form of the wave. Okay, right? You start with the form of a wave, a plane wave, as in you can start with a form of a psi, right, including both x and t, a general complex form, and you would notice that that equation would satisfy that form of the function, the form of the wave function would satisfy this equation. All right. Now I might be rambling. Okay, the last few sentences might not be 100% clear to you, but in a tutorial I will demonstrate precisely what I mean right now. In other words, how we start with a particular form of psi, right, and how that satisfies this equation, and how we can justify this equation. For now, please take this equation for granted. The only thing we'll do is we'll just try to do a simple dimensional analysis. That's important, right? Recall, any equation you give in physics or chemistry, right, always check the dimension or dimensionality of the equation. All right. So again, we don't know what the wave function's unit is, right? We'll just give it some wave function unit. Okay, right? And this is going to be corresponding to joules. So the whole thing here, right? This should correspond to, so this is per time, and this is some wave function unit. This whole thing should correspond to some joule times some wave function unit. I'll just call it WFU, some wave function unit, right? Recall, even in the previous lecture, right, when we started with the wave equation, I did not talk to you about what the unit of the wave itself is. I just said, the wave is a dimensionless quantity. Okay, that is what I had told you in the last class. Okay, now in the tutorial, we'll be looking at the units of these wave function in greater detail. For now, let's just take it as some wave function unit. It could be no units also. Okay, right? So this is joule times some wave function unit. Now this whole thing should also be some joule time wave function unit, right? Now I is, of course, right? What is I? I is a number, right? Yeah, so numbers are dimensionless. That's ruled out. H bar is h over 2 pi. 2 pi is a number, so that's also ruled out. So your h is going to be E equals h nu, from the Planck relationship that we obtained. If E equals h nu, your h is going to be, E is joules, right? So joule per second. So that's going to be joule second, right? So this is joule second. And this is going to be, like, say, something like some wave function unit again, divided by per second, because there's a time there. So this is joule times wave function unit. So dimensionally, we see that the time dependent, this is called as time dependent, TD for time dependent. time-dependent Schrodinger equation to understand the time evolution of systems. Are we clear? Okay. Now, we're not interested to solve this equation in particular because it really depends on the form of the Hamiltonian. See, what I've hidden from this equation, okay, what I've hidden in this equation, the way I've written it here is that the psi, in other words, the wave function, it has both a spatial dependence and time dependence, all right? But the Hamiltonian itself can be independent of time, as we saw in the time independent case, right? Or the Hamiltonian can also have a time dependence, okay, right? So, depending on whether the Hamiltonian contains the time dependence or not, the solution, the form of the wave function is also going to be changing. All right. So let us not worry about those details, and please understand for now that if you want to get a static picture, that is, you want to understand the behavior of quantum mechanical entities at any given point in time, you shall be using the time independent Schrodinger equation, right? Which is nothing but simply a recasting of the conservation of energy principle for a quantum mechanical system. And if you actually want to understand the time evolution of the same system, right, you use the time-dependent Schrodinger equation. All right. So this is the summary and the gist for when to use the time-dependent Schrodinger equation and when to use the time-independent Schrodinger equation. All right. Now, in this course, what we are next going to see, okay, is that recall that the whole idea of why do we even study about these introductory aspects of quantum mechanics and astrochemistry? Well, it is to see how light interacts with matter. Okay, right? So as part of it, in the next few modules, we shall be, just solving this equation for a few simple systems. It won't take more than 1 or 2 lectures max, okay, to understand some general principles which will be very useful to understand the interaction of light with matter. Okay, right? We no longer need to worry about this equation in this course, okay, in this specific course, because the principles that we shall be using for spectroscopy shall be mostly based on this equation. In fact, this equation, that is the time independent equation, can be obtained as a subset of the time dependent equation, right? We can show that in tutorial. We can show that in a tutorial where we can take a specific and easy form of the Hamiltonian, which is like time independent, okay, right? And we can show that this equation emerges from this, okay? So we need not worry about the distinction between these two equations at this stage. I repeat once again, okay? And what we shall be focusing on hereafter is going to be to solve this equation for a few systems to understand some principles that are relevant for how light shall interact with matter. Okay, so on that note, I will delete all this part and I'll tell you where we are going to, what we are headed towards in this course. For very simple systems, okay, right? Okay, that's it. So to understand light matter interaction and to understand some principles which are used in spectroscopy, we're going to solve some this equation for just 2 very simple systems, and we're going to use the results obtained to generalize that to several other systems, okay, right, which are useful in understanding spectroscopy and therefore light matter interaction. All right, okay. The first system we shall be considering, is what is called as a free quantum mechanical particle, right, moving along now. This is the first system, right? So the first system we are considering is a free quantum mechanical particle moving along the x direction, with some arbitrarily assigned potential energy to be 0. It's a hypothetical entity, okay? Just imagine some hypothetical quantum mechanical entity, right, moved free along only one direction, right? In other words, it's just moving along a straight line. Okay, right? Now we're going to our idea is to solve this equation, the h psi equals e psi, for this system, right? For this system, and try to obtain some insights based on this. Okay, all right. Now we know what equation we have to solve, right? That's already given to us. That is h psi equals e psi. And so in this equation, right, you have like three terms, correct? You have like h, psi, and e. Are we fine? We have three terms, h, psi, and e. What is our objective? Our objective is to somehow solve this equation, right? Solve this equation to get energy. But to solve the equation, we need to know what function we are using, right? We only know the form of the Hamiltonian, right? The form of the Hamiltonian, that is your h is nothing but this, right? How did I get this? Because from the full term, this is nothing but potential energy plus kinetic energy, right? And that this is the kinetic energy term, and I've chosen my potential energy already to be 0, correct? So therefore, this is my Hamiltonian. This is easy. So I've obtained this. Now rewriting this equation. In other words, I need to solve this equation. Right? And find E. That is my objective. So I must first of all, solve this equation, okay, and find E. Now, what does solving an equation mean? Solving an equation means substituting the value of a variable in an equation, right, and get the unknown term. So this is the unknown term. But hey, wait. I said this is the unknown, but do we actually have any idea about the form of the wave function itself? Do we know anything about the form of the wave function here? We don't, right? We don't. Now, why do we not know? Because I haven't told anything about the form of the wave function other than the fact that, hey, this is a quantum mechanical particle moving. When I say quantum mechanical particle, it of course has both wave and particle nature, okay? So instead of using this word particle, okay, I would be better off using this phrase entity, okay, right? Because when I use particle, you may be confused. Oh, does it not also have a wave nature? Of course, it's a wave particle, but for just ease of use of language, right? I just put it as quantum mechanical particle. So strictly speaking, it should not be particle. The phrase entity would be a better, better word to describe the scenario here. Okay, all right. So I need to solve for E here, but I don't even know what my psi of x is. Okay, but hey, this is where paying careful attention to the equation helps. Okay, right? Now, what does this equation tell you? This equation tells me that there is of course a constant here. Okay, you can club this constant here also. This is going to be minus 2me by h bar square. Okay, right? If you put this constant here, and once you look at the constant over here, noticing that like none of them is 0. Okay, h bar is not 0, m is also not 0. Okay. Now, when they are not 0, you know that you have a differential equation of the form which tells you that I differentiate a function 2 times. Okay, I differentiate a function 2 times and I get back the same function. Are we good? So I differentiate a function 2 times and I get back the same function. Now, what functions can you think of? What are the functions you think of which satisfy this criterion? That after you differentiate it twice, you will be getting the same function. What functions can you think of? Yeah, sines, cosines, and exponential functions, right? And so you can think of something like if y equals e to the power x, your dy by dx is also e to the power x, and your d2y by dx2, that is like the second derivative, is also going to be e to the power x. If it's e to the power ax, right? Or it's going to be like the first derivative is going to be a to the power ax, and your second derivative is going to be a square e to the power ax. Correct? In any case, right? In any case, the same function is retained. Likewise, if you choose the sines and cosines also, if you choose sines and cosines, even in that case, you understand that the first derivative of sine is going to be cosine and the second derivative is going to be sine. Okay, right? Likewise, if you choose, like cosine, it's going to be, the first derivative is negative sine, and the second derivative is going to be negative cos, because the negative is already obtained in the first derivative. Okay, right? So overall, a combination of sines and cosines, right? So psi of x might be some general combination of a sine kx plus b cos kx, where a and b are any complex numbers. It can be any complex numbers, and k is any real number. All right. So I just stop this class at this stage, right? Noting that the solution for for this Schrodinger equation for a quantum mechanical system moving along x direction with v of x equal to 0, right, which is called as a free particle. It's free particle because it's free. Okay, there is nothing binding it. It can move along it can move for any distance along the x direction. Okay, so this is called as a free particle, right? And for this free particle, the wave function might be a sine kx plus b cos kx. We'll continue from this point in the next class. Thank you so much.